All right, so we're going to talk a little bit about the error that we get when we truncate a Taylor series into a Taylor polynomial and how to deal with those errors. And there are three types of error bounds that we are going to look at. One is specifically for geometric series, called the geometric series error bound. The second one is specifically for alternating series. It's called the alternating series error bound. And the last one is for basically any Taylor series, and it involves this thing called Taylor's theorem and blah, 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 and it ends up being called the Lagrange Error bound. I would say that 70% of the time on the AP test, if they ask about error bound, they're going to be nice to you and give you an alternating series error bound question, and those are really easy. And it's like the other 30% of the, well, I would say like 28% of the time, they're going to give you a Lagrange error bound, which is the unpleasant one that no one wants to deal with. And then the other 2% of the time is the geometric series error bound, which is also exceptionally easy. So that's where we're at. So we're going to start with the geometric series error bound. This is only good if we are talking about a geometric series. Okay. So if we are taking a series, let's take this series 1 plus x squared plus x to the 4th plus x to the 6th plus x to the 8th and so on, which we should know is the sum from n equals 0 to infinity of x to the 2n, right? Or the series for 1 over 1 minus x squared. Right, so the same thing, right? 1 over 1 minus x squared, n equals 0 to infinity of x to the 2n, just by our basic, like going straight from 1 over 1 minus x is x to the n. My board made a weird noise. You probably all heard that. So then we just plug in the x squared, becomes x squared to the n, x to the 2n. And we truncate it after the term x to the 6. So we truncate it after 4 terms. Okay. So what would the series, let's write out what the series would look like, and then let's write a couple terms past the truncation. So our series looks like 1 plus x squared plus x to the 4th plus x to the 6th. That's where we're truncating. We'll do that in a second. And we would have x to the 8th and x to the 10th and x to the 12th and so on. Do y'all agree with that? Yeah, okay. So we truncate here at x to the 6th. We're going to use just this the 6th degree polynomial, this Taylor polynomial, to approximate the value of this function at some x value on its interval of convergence, or some x value between -1 and 1. And so the question is, about how much are we off by, or what is the maximum amount that we could be off by? Okay. And so the amount that we are off by, this is our approximation, right? This is the actual value. I can spell the word actual. If I can spell your last name, I can spell the word actual. I'm not talking to any of you in the Zoom about your last names, because your last names are all easy to say. Oh, look, there's Wittenberg arriving late to class. So what is our error? Okay, effectively, yeah, it's the sum from, what did you say, from 4 to infinity of x to the 2, right? That's what our error is. And let's take a look at what that term or what that series sort of looks like. Let's write it, I'm going to write it on another page. X to the 8th plus x to the 10th plus x to the 12th, and so on. Right, everybody agree that that's the error? Yeah, everybody agree with that? Right there. The approximation, the actual value, the error is what's the difference between. Yeah, everybody in Zoom good with that? Yeah.
Yeah.
All right. What is the common factor of all of these? What? I mean, x squared is a common factor of all of these. I mean, there is a common factor of 1 also. What? Let's try this. What can I factor out of all of these terms? X to the 8. Yeah, Ryan showing up late, but bringing some knowledge here. Where I take out the x to the 8. And what are we left with if we take out the x to the 8? 1 plus x squared plus x to the 4th, and so on. What is this right here. This is our original series, isn't it? So what is our error? Our error came out to be, what was this? This was this is the first term after we did what? After we truncated our series, right? So our first term after our truncation times the original series. That is the geometric series error bound. Okay. The geometric series error bound is the first term after the truncation times the original series. And we have to keep in mind here that if we're talking about a geometric series, the geometric series only converges when the common ratio is between -1 and 1, which means that those values, that when you plug in those values of x into there and raise them to these powers, these are actually small numbers, right? These are this number, x to the 8 times 1 plus x squared plus x to the 4, and so on, is less than the actual value of the series because all the values of x are between -1 and 1. Right? Make sense to everybody? People here good? Good? Yeah, okay. People in Zoom, are you good?
Yep.
Very good. Wow. Okay. So let's see if I put it. I didn't put another one here. Okay. Let's suppose I don't know. Let's say how about we took these series. This is an easy one. The sum from n equals 0 to infinity. Just make sure you have the idea. X to the 3n. And let's truncate using I don't know, let's truncate using a 6th degree Taylor polynomial. And we're going to evaluate, we're going to find the error evaluating x equals 1/2. So let's see if we can do this. That'd be fun, huh? Yeah. You guys think you could do that? Yeah? Yeah? Derek, could you do that? Maybe. That's better than no. I'll give you guys a second to see if you can work through that. Yes, finished with that? Zoom finished? Zoom done. Man walk now. No man walk. Confused? Yeah. You confused. Not you. You. You confused. Yeah. Man no walk. Man no walk. What? Man no walk. No. No man walk. Man no walk. No. No man walk. All right. What do we get here? We wrote out our series, or our polynomial, sorry, it's 1 plus x cubed plus x to the 6th, right? Okay. And so our error then would be the next term times the original series. And what's our next term? X to the 9th, right? So we should have x to the 9th, and it should be times that original series, which is the sum from n equals 0 to infinity of x to the 3n. We would note that if we're looking at x equals 1/2, what's the common ratio there between the terms? Or what is the series, what is the function that this series represents? Well, what's not even x, yeah, the function itself. 1 over 1 minus x cubed, right? So this should become x to the 9th over 1 minus x cubed. And if we're just going to evaluate that at a half, that should become 1/2 to the 9th over 1 minus 1/8. So we got, I don't know, whatever that comes out to be. Oh, that. What? I don't know what you're saying. I disagree. I believe it's 7/64. Does that sound right to anybody? Yeah? Yeah? Just based on some rudimentary arithmetic in my brain. Oh, yeah, it would be. All right, fine. My arithmetic was bad. 64. 404. All right, that sounds good. Okay. Yeah, you're right. Okay. Yeah, you win. You win. Good job. Okay. 1 over 448. Everybody agree with that now? That was me and Noah having an argument. It's like me arguing with my child, whose name is Noah. Except this was a lot more peaceful. All right, everybody good there or no? We feel like we could do that? All right, wonderful. Okay, the next type of, there's a big circle there for no reason. Circle there. The next type of error bound that we're going to talk about is called the alternating series error bound. The alternating series error bound works only for a series that alternates. That should be pretty obvious. Okay? The alternating series error bound. This is the easiest error bound to find. Okay. The amount that any alternating series that is decreasing, the terms are decreasing in absolute value, so they're getting smaller. If you take the absolute value of them, like down here, 1 minus a half plus a third minus a fourth, the individual terms, that's supposed to be a half and that's supposed to be a third, those are getting smaller, right? A half, a third, a fourth, regardless of the oscillation between positive and negative. Okay? So 3 criteria must be met for this to work. Number 1, the terms alternate. Number 2, take the absolute value of them and they are decreasing in value. Number 3, they must be approaching 0. Right? So 1, a half, a third, a fourth, a fifth, a sixth, a seventh, an eighth. As we go towards infinity, that's 1 over infinity. It's approaching 0. So for this particular series that we're looking at, all 3 of those criteria are met. Would you all agree with that? Okay, good. All right. So, and if we have those 3 criteria met, the error bound is always 100% of the time just going to be the next term after your truncation. So the truncation after n terms, the bound on that error is the next term. The error will never be more than that next term, or the absolute value of that next term. Whenever we talk about error, we always talk about it in the positive term as a positive value, so we always take the absolute value. So that's the error for the alternating series error bound. And we're going to look at, we're just going to look at this series 1 minus a half plus a third minus a fourth that we know converges to natural log of 2. How do we know that converges to natural log of 2? What is the series for? And you should have this in that series you should know paper. What is the series for the natural log of 1 plus x? Should be the sum from x to the n plus 1 over n plus 1, starting at n equals 0. Does that look good to people? Jenna took it from her notes, so I assume it must be right. All right. So if we were to write out this series at x equals 1, which we determined that it did converge at x equals 1 by looking at the values, right? We said this converges for -1 to 1, inclusive on the 1, but not on the -1 because you can't take the natural log of 0, right? If we look at this series at 1, if we plug in 1 for x, then this just becomes -1 to the n over n plus 1, right? And so if we start at 0, that's -1 to the 0, 1 over 1. There's our first term, 1. Plug in n equals 1, that's minus 1 over 2. And then it becomes plus 1 over 3 and minus 1 over 4 and so on. This is just the series for natural log of 1 plus x evaluated at x equals 1. Everybody see that? Should be something that we hopefully see. People here seem good. People at home, are you good?
Yeah.
Okay, good. All right, so we know that this converges to the natural log of 2. Somebody give me a reasonable approximation for the natural log of 2. It's like 0.693 something, I think. I know, but I'm just ballparking it here. Well, that's not exactly right. Okay. There's a half. 0.693. Let's see, that'd be right there. Yeah, so this is our true value, natural log of 2, which is about 0.693. All right, now let's think about what's going to go on here. We know that this series converges to this value of natural log of 2. We also know that it oscillates. So we know that it's going back and forth, or alternates. We know it's going back and forth from positive to negative terms. And if it's going to converge to natural log of 2, each successive term that we add or subtract has to go from one side of natural log of 2 to the other side of natural log of 2. And then back to the right of natural log of 2 with the next term, and then back to the left of natural log of 2, getting closer and closer and closer each time. Would you all agree that that's true? That's how we're converging to natural log of 2. So every term must be getting us closer. And if we're adding and then subtracting, we're going to have to go back and forth beyond that value. Would you all agree? At home, people here are nodding their heads. So at home, you good with that?
Yes.
Okay. So our first term, if we truncate at 1, which we're not going to do because that's just stupid, but if we truncated it at 1, we're right here. True? And the next value that we put in is -1/2, which tells us we must go back to the left of natural log of 2, right? Over to 1/2. Right, so here's one term. After 2 terms, we're going to be here. Okay, we're going to be at 1/2. And we'll note that when we were at 1, the error that we were off by is less than, this would have been our error, right? That error is less than this next term because that next term is on the opposite side of natural log of 2. Do you all agree with that? Okay. And the next term had to bring us to the left of natural log of 2. Jenna, you okay with that? You sure? Yeah? Okay. All right. Your eyes looked not quite sure. So, all right. Everybody at home good with that? Cool. All right. Good job. All right, so our next truncation that we might do would be after 2 terms. Well, that puts us here at 1/2, right? And then our error would then become this value, true? Whatever that value between 1/2 and 0.693 is. But our next term plus 1/3 has to take us back on the right-hand side of natural log of 2. So 1/3 is going to bring us, I know that's not quite right, but we'll call that a distance of 1/3 there. It's going to bring us over here. Right? That's going to bring us over here. Our error was less than that next term. Same thing's going to happen. This is where we're at after 3 terms. Well, now this is our error. And if we subtract the 1/4, that's going to bring us over here to the left of it. And so our next term was, again, more than our error. And that's going to continue happening every single time, because every single time we have to go back and forth above natural log of 2, then back below natural log of 2, then above natural log of 2, then below it, in order for us to converge to that specific value of natural log of 2. Does that make sense? That means the error is going to get smaller each time. That is correct. The bound on the error. So we're not talking about the exact error, because this is 1/4 is not the exact error if we truncate after 3 terms. Right? 1/3 is not the exact error after we truncate after 2 terms. It's just the bound on it. We know that the error will always be less than that next term. So we can know at least we can know at least how accurate we could be. Right? We're more accurate than 1/3 off after 2 terms. We're more accurate than 1/4 off after 3 terms. We're more accurate than 1/5 off after 4 terms. Does that make sense? Yeah, basically. Everybody good there? People here good? Yeah. Zoom good? Good Zoom? Zoom good good? Good Zoom good?
Zoom good.
Zoom good. Man, no walk. Zoom good. Okay. Man, no walk. Okay. I wanted to do, did I want to do another one of these? That's easy enough. Do we need to do another one of those? If I give you an alternating series and I ask you what's the bound on the error, you'll just tell me it's the next term. Should be easy enough. Okay. Like if I said, what's the bound on, I will just real fast through this. I said, what's the bound on approximating, I don't know, approximating sine of 2. Sure, sine of 2 using using a 4th. No, so it's using yeah, okay. We'll say using a 5th degree Taylor polynomial. Shouldn't 4 wouldn't make a lot of sense for that. So. Now, what's your series for sine? Your series is sum from n equals 0 to infinity of yeah. Good. That series alternate? Yeah. Terms are decreasing? No, that's not going to work. Terms aren't decreasing, are they? That doesn't work. Darn, should have chose sine. All right, never mind. Don't use sine. Ignore that slide. New slide. Should have picked one where the terms were decreasing in absolute value. How about use the series -1 to the n. We'll just do -1 to the n over n squared plus 1. That works for sure. Times x to the times x to the n at x equals 1/2. That'll do it. All right. And let's use a what should we do? We should do a let's truncate at 3rd degree. So use an alternating series error bound to tell me what that error should be. What are we looking at here? Should just be the fourth term, right? The error should be the fourth term because this series alternates, -1 to the n. It's decreasing in absolute value, and it's going towards 0, right? These are definitely decreasing because if x is a half, it's 1/2 to the n, which is getting smaller, and n squared plus 1 is getting larger, which is in the denominator. And so if the numerator is getting smaller and the denominator is getting bigger, it's definitely getting smaller. And it's definitely going towards 0 as well. And so effectively, we've got a 2 to the n and an n squared plus 1 in the denominator. So it's definitely going towards 0 as n goes towards infinity. So what's our fourth term? Our fourth term should be the absolute value of -1 to the fourth, 1/2 to the fourth over 17. And that's just 1. The absolute value becomes insignificant. We have 17 times 16. What is that? 272? So we are off by 1/272nd if we approximate the value of that series using at x equals 1/2 using a third degree Taylor polynomial. Good? Zoom good? Good zoom?
Good, good.
Good, good, good zoom, zoom, good man walk, man no walk. Okay. All right. Now for the last little bit of this. So for any other series that does not fall into the geometric series category or does not fall into the alternating series category, you will need to use what is called the Lagrange error bound. And I will give you guys a second to read through this, and then we will sort of talk about what all of this stuff means. And we're going to use it to prove that sine x converges for all x. And then we're going to really do it numerically a couple of times also. So take a second to read through that, and then we'll talk about it. I'm going to go back to how did this say? We had a page in here that I wanted before that. There it is. Okay. Read that page. That's the page I thought was up there. This is the page I wanted up there. Somehow I put another page in after that one and was doing it already. Zoom, read that page. Class read. Red. Class red. Zoom red. Still reading. Zoom read. Read zoom. Zoom read.
Still writing it down.
Zoom right. Okay. Zoom read and write. Read, write, arithmetic. Like elementary school. We can read, we can write, we can do arithmetic. We are well-cultured first graders. Or something. I don't know. I've seen my son's second grade class. Some of them have trouble with all three of those. Still. You got an apple over there in your backpack there? Yes. Is it sliced up? Yes. Is it a red delicious apple? That's what mine is, because my kid keeps bringing them home from school. I wouldn't choose them, but he comes home every day with this giant stack of food. The school just gives it to him as he leaves. They're like, just take this. Like we're not going to feed him or something. I don't understand. It's got like a tangerine. It's got an orange. Yesterday it had 4 apples in it. What is my second grader going to do with 4 apples, an orange, and a tangerine on top of a frozen burrito, a frozen empanada, a banana chocolate chip nut bread? Yeah, that was good, right? It had a cherry flavored applesauce. It had a I think it's just got a hint of cherry in the applesauce. It had, what else did it have in it? Oh, God, so much stuff in there. What? Oh, yeah, it has chocolate milk. It has regular milk. It had 2 small cartons of apple juice. I'm just like, they're giving this to every kid that walks out of the elementary school if they want. They just hand you a sack of food? Can they give me a sack of food? I will never have to go to the grocery store again. This is great. I'm just like, my older kid gets a sack of food. My younger kid gets a sack of food. I get a sack of food. Yeah, 12 apples. That's a whole dinner. No, every student in the district. It's, yeah. The same thing? Probably the exact same thing. Because 12th graders and 2nd graders eat the same amount of apples each day. Less apples. Yeah, it's not usually 4, but one day, yesterday. 4 full apples. Just whole apples, 4 full apples. Yeah. It was great because the Zoom people, you don't care about any of this, I'm sure. And this is all going on the recording. So everybody, if you're missing out on this recording, you can go back and like listen to it again. They really absorbed it all. Yeah, so I was gonna make carnitas, and my recipe that I use for carnitas requires orange juice. I didn't have any orange juice, and I was like, I have to go to the store and buy orange juice or an orange at like 6 in the morning so I could put my carnitas in the slow cooker. This was like sometime last week. It was like Wednesday or Thursday of last week. And then all of a sudden, he had an orange. My kid had an orange in his giant sack of food. That sometimes he brings home his giant sack of food and just leaves it sitting on the kitchen table. And if I don't get around to putting it all away, then it just sits there all night. So all of his frozen stuff was disgusting. I had to throw it away. It's just been thawing and sitting there all night. But there was an orange in it. And so I just sliced up the orange, squeezed all the orange juice into my carnitas, and we had carnitas for dinner that night. Good times. I'm sure everybody cares. It was a lifesaver. I thought, what am I going to do for dinner? Do I have to go to the store at 6 o'clock this morning? No. Orange juice for the carnitas. Good. All right. Speaking of that, we should learn. Okay. So if we take a Taylor series and we truncate it into a Taylor polynomial, it's not that far. How about there? Right there. We're going to truncate it right here. This is our polynomial. And here is our remainder. Okay. And we can say that remainder that we end up with is going to be, no matter what, less than or equal to this. And we're not going to go through the full proof of this because we just don't really have time because I spent too much time talking about orange juice, so I wasn't going to talk about it anyway. But this term here represents effectively the next term in this series evaluated at some value C that is between A and X. And C is the value between A and X that makes that derivative, that n plus 1, we'll just say it makes the n plus first derivative of f the largest it could be. And that is all there is really to this Lagrange error bound. We need to take the next term, x minus a to the n plus 1 over n plus 1 factorial. That's just our standard Taylor polynomial formula that we've been using, right? This is the next term. That's why it's n plus 1. And then multiply it by the n plus first derivative at whatever value c between a and x that gives us the largest value for that derivative. Does that make sense to everybody? Okay, cool. You okay, Derek? Okay. So, I don't know, sometimes people have trouble with this. Sometimes people have trouble because they have difficulty finding what value of c makes that derivative the largest that it could possibly be. But we will be able to figure that out because we are smart individuals in this class, right? Right, Zoom? Smart? Zoom smart? Smart Zoom. Okay. So, everybody okay with that? This is the Lagrange error bound. That is the largest possible value that our error could be. Our remainder will always be less than that value. Okay. So what we're going to do is we're going to take the series for sine and prove that sine x converges for all real x. Now, I know we already said that it is, and we even said it converges for all complex values, and we also did all this fun stuff with it. But we're going to prove that this is true by using the Lagrange error bound, right? The bound that we can find on a Taylor polynomial by truncating after whatever number of terms that we want to, okay? So if we think about this, we could say that if the remainder approaches a value of 0 as n goes towards infinity, then this should tell us that the series converges for that value of x. Right, for whatever value of x that we put in. So if we can prove that for any value of x, the series for sine, the remainder on the series for sine, should approach 0, that should tell us that effectively, no matter what x value we put into sine x, the remainder is nothing. The remainder is insignificant as n goes towards infinity, and therefore the series should converge for that x value. And so we can show that's true for all x, then we can say that it converges for all x. Does that make sense? Or no? Yes? Zoom makes sense?
Yes.
Yes. Okay. So our remainder should be less than or equal to what term then? It should be the n plus first derivative at some value c, right? True? Times x to the n plus 1 over n plus 1 factorial. True? That's what it should be. Y'all would agree with that? That's our next term. That's what we just said. Well, first off, as n goes towards infinity, which of these things grows faster? Does an x to the n plus 1, so exponential, or a factorial? Which one's going to grow faster? Factorial. And that's a very important point to note. A factorial will always grow faster than an exponential. Okay. A factorial always grows faster than an exponential. Everybody good with that? That should hopefully make sense, right? Because x is just some number, and eventually, even if I have 10 billion to the infinity, right here I've got a bunch of numbers that are way bigger than that I'm multiplying also. I'm multiplying the same number of terms, but these get bigger than the exponentials do because these are just the same values, and these are. Does that make sense? Everybody good with that? Okay. All right. Cool. So that means that as n goes towards infinity, this piece of it is approaching 0, right? This is approaching 0, no matter what x is. True. So then the question is, what about this piece of it? Well, if we're talking about the function sine x, what are the derivatives of sine x look like? They're all of these forms, right? The n plus first derivative is going to be of one of those 4 forms. And what can you tell me about all 4 of these things? They're all less than or equal to 1, greater than or equal to -1. And therefore, I've got 0 times some number between -1 and 1, which should give us 0. So no matter what x value I plug in, this factorial growth outstrips the exponential growth, giving me a limit as n approaches infinity of 0. My derivative in here does not add any sort of factorial growth into the numerator. It just adds in some constant between -1 and 1. Therefore, this limit is still equal to 0. Therefore, this converges for all real numbers. Conceptually, does that make sense? The likelihood of you having to do that on the AP test is small, but that's sort of the basic idea of how it works. Okay, cool. This is what we just talked about, right? This is exponential growth. This is factorial growth. Factorial growth is more rapid than exponential growth. Then we just need to look at what happens as the derivative approaches, as n approaches infinity of the derivative to see if this adds in something that is going to be enough to overpower this factorial growth, which is rarely going to happen. Right? I mean, the chances of having a derivative with a factorial in it are small, especially on the AP test. They're not going to do that. So, good? Okay. Cool. We are going to not worry about this. This is something that is not really required for you on the AP test. I usually talk about it. It's called the remainder bounding theorem, and it's going to let you prove things like e to the x converge for all real x. Also, we just sort of looked at it and said it looks like it does, but this will allow you to prove any function of e or some other functions that converge for all x. What we're going to do is this. We're going to try to use the alternating series test as well as the Lagrange error formula to find a bound on the error of the series natural log of 1 plus x at 0.1 after 2 terms. We're going to do it both ways, both alternating series and Lagrange. So first thing is, I trust that you all could probably do the alternating series test on your own. Okay, do that. You guys do the alternating series test, and then we'll work our way through the Lagrange error bound together. How do we do with the alternating series one? Finished? Not yet. what's the first term of the series for natural log of 1 plus x? What? I can't hear what you're saying. Like in general, the first term. What does your series for natural log of 1 plus x look like? Right, so what's the first term? Uh-huh. No. It equals x. The first term of that series is x, right? This is your series. I mean, you're right about, did you guys tell me with that n equals 1? Like this? Yeah? I mean, that's fine. Or I don't know, did we do it like this? I don't remember how we wrote it out. Okay, either way, I mean, same thing. Right? Either one of these is going to give you effectively the exact same thing. Right? First term is x. Second term is minus. That's our first two terms. We truncate. Next term would be x cubed over 3. That's our bound. Our bound on the air is the term using x cubed over 3 with an x value of 0.1. So it's just 0.1 cubed over 3. That's all it is. And what's 0.1 cubed? 0.1 cubed should be 0.001 over 3, which should be, what is that? 0.00033333333, and so on. Yeah? Or 1 over 3 times. Sure. That's fine too. Good? Everybody good with that? Sure, any of those numbers will be fine. Yep. All right. Now, what about using the Lagrange error bound? So, the Lagrange error bound says that our remainder should be less than or equal to the absolute value of the n plus first derivative. In fact, if we're talking about after two terms, we're going to be looking at the we had x minus x squared over 2 plus x cubed over 3, right? We're truncating here. What are we going to need to use? We should be using our third derivative, right? So third derivative at c times x to the third over our n plus 1, right? Which what is our n? Our n is 2. So over 3. Now this is n equals 2. We started n equals 0, n equals 1, then n equals 2. Right? N equals 2 is the term we're using. It's n plus first derivative, third derivative, x to the n plus 1, third power, n plus 1, 3 in the denominator. Everybody good with that? Zoom good with that or no? You guys have been awfully quiet the last 15 minutes. Yeah, that's it. Okay, I'm waiting. As requested. Oh yeah, sorry. No. Yeah. No, it's 3 factorial. No, the bound is n plus 1 factorial. Yeah, doing Lagrange error. So our bound is, yeah, sorry, I forgot the factorial, but yes, correct. X to the n plus 1 over n plus 1 factorial. Everybody's good there? Okay. All we need to do then is figure out what the third derivative of our function is. Well, we're talking about the function natural log of 1 plus x. So what's the first derivative? 1 over 1 plus x. What's the second derivative? Negative 1 over 1 plus x squared. And what's our third derivative? should be positive 2 over 1 plus x to the third. Good or no? Okay. So now we are interested in what x value is going to make this the largest. And because the interval that we're talking about of convergence here is -1 to 1, right? We need some, we need whatever is going to make it the largest on, we're talking -1 to 1 inclusive, but we're approximating it at 0.1, so it's got to be something between 0.1 between 0.1 and 0. Right, yeah, that makes sense. 0.1 and 0. So what value between 0.1 and 0 is going to make this thing the largest? Why 0? Right. The larger our denominator, or sorry, the larger this x value becomes, the larger this thing becomes. We cube it, it becomes larger, makes this thing smaller. We want this to be the biggest it could possibly be. The biggest we could possibly get for this, for the whole thing, is the smallest we could possibly make this. Smallest we could possibly make this is going to be 0. Right? And so what's that give us? It gives us a value of two. So f third derivative at c is going to be at 0. That's going to give us 2. So we're going to have 2 times 0.1 cubed over 3 factorial. And what does that give us? The 3 factorial has got a 2 in it, which cancels with that 2. And we end up with, once again, 1 over 3,000. Same thing. Does that make sense or no?
I have a question on the interval. So when you're talking about what x value makes f to the third degree largest, the interval for those x values is 0 to 0.1.
So I sort of said that, but that's not quite entirely right. So our x value is, the x value that we're evaluating at is 0.1. When we talk about that interval, we can really just look at on the interval for which this thing converges. Looking on 0 to 0.1 is not really what we want to do. We can really look between -1 and 1 for what makes this thing become the largest. I mean, that's anything between -1 and 1.
Okay, so it's the same as the interval of convergence then.
Yes. But generally what you're going to want to look at is, we're talking absolute value in here. So you can sort of ignore the negative values. So really what we're looking at is just 0 to 1, because we're going to be taking the absolute value of it anyway. So really, what's the best way to say this? Go from the center of your interval of convergence, so which will, in this case is 0, and look for the value between 0 and the end of that interval of convergence that includes that 0.1 that's going to give you the largest value. That help?
Yeah, so it's basically only positive values on the interval of convergence. Is it, can I simplify it to that?
Okay, the right hand values doesn't sound right. The values that make it a positive value. So sometimes those values might be negative values. Like if your interval of convergence is only negative numbers, you need to pick the the values that will make it a positive large number. Does that make sense?
Yeah, okay, that makes sense.
Yeah, so it just depends on what your interval of convergence is. What? Why did I use 0.1? Why we look between 0 and 0.1? Yeah, because that's part of that interval. Okay, all right, okay. So okay, I have. Let me restate all of this. Okay, this is because I think I have sort of bungled what I've said. Is that a word I'm allowed to use? Bungled. Okay. Sometimes there's words and then they have like meanings from like hundreds of years ago that are like politically incorrect. Bungled is okay. I hope so too, because I've used it like 12 times now. If it's not, I apologize to whoever I've offended. We're talking about the C that is on the interval between A, or we'll say the C that is between A and X. So I have misstated this. The C between A and X. A is the center of your interval of convergence. And X is the given value. So I think I said 0 to 0.1 is what we were looking at, right? And that is what it should have been. Okay. For this particular one, we are looking 0 to 0.1. That's a good question. I shouldn't have said that. Yeah. So this is what you need to do. C is between A and X, where A is the center of your interval of convergence and X is the given value. What I originally said is correct. And then what I tried to restate when I think that was Sean was asking was wrong. I restated it improperly and incorrectly. I don't know. We will because he asked me to. And then I think, I don't know, maybe I just was starting to do it again anyway. I don't know. Good question. This is what it should be. C is between A and X, where A is the center of your interval of convergence. So in our case, that's 0. X is the given value, which is 0.1. So we're looking at the largest value between 0 and 0.1 for this particular one. Does that make sense? Forget everything I said before. Except for the original thing that I said, which was this. Yeah. Everybody good with that now? Sean, good with that? Everybody good with that?
Sure, yeah.
Okay. Perfect. Good. That's what you should do. Say that again. What? Oh, you're talking. Oh, yeah, because this gives us, we take the absolute value, we only need one side. That's what. All right. Everybody good there now? Okay. All right. Let's see. We got like 2 minutes. Let's see if we can do this. I was hoping to get through this one. So we'll see if we can get through this and then we'll be done with this section for today. So take a look. See if you can come up with, there should be an absolute value there that's not really showing up. See if you can show that this value, f of x minus the second degree Taylor polynomial. What is f of x minus the second degree Taylor polynomial? This is the remainder, and they will often write it out as such. The function minus the Taylor polynomial inside absolute values. That's the remainder. They want you to show that the remainder is less than 0.05. So what are we looking at? We're looking at the in plus first derivative, since we're using this as a second degree Taylor polynomial or second order Taylor polynomial. That means n plus 1 is 3. So we're looking at a third derivative. So our remainder ought to be less than or equal to the absolute value of the third derivative at some value c times our x minus our a. What is our x minus our a here going to look like? What is our a value? 2, right? Our a value is our 2, because that's what we're centered around. So this should be x minus 2 to the n plus 1. It's n plus 1. We know that that's the third, right? Over 3 factorial. Everybody good with that? Okay. Then we're talking about specifically the third derivative is always less than 2.3. So what's the largest possible value that the third derivative could be? 2.3. So we'll put in a 2.3. We know it's less than that, so we'll put in the 2.3. What goes in as our x value? Our x value should just be this 2.5 value that we're ending our interval at. So this becomes 2.5 minus 2 cubed over 3 factorial 6. So that's our remainder. So we end up with 2.3 times 1 over 2 cubed, or times a half cubed, times 6. And what's 2.3 over 48? Approximately, as a decimal. 0.048. And since we got 0.048, that tells us our remainder is less than 0.048. 0.048 is what in comparison to 0.05? It is less than 0.05. So if our error is less than 0.048, our error must be less than 0.05. Does that make sense, everyone? We feel okay about that? The same problem? Yeah, we are recording. That's true. Okay, so once more, just to go over it. The remainder is your absolute value. Next derivative, that's third derivative at c, x minus a to the n plus 1 over n plus 1 factorial. And so our x value ends up being 2.5. Because that's 2.5 is the largest, the value that will make this thing the largest, right? If I plug in 2.5. For any x in this interval. Right. Correct. Like if I put in 2.1, I get 1/10 to the third, which is going to make this a much smaller value. But the largest it could possibly be is 1/2 to the third. Does that make sense? Does that make sense to everybody? Or no? Why we chose 2.5?
Makes sense.
Okay.
That's also the same reason why you chose 2.3 for the third derivative, right? Because that's the largest value.
You know that it's the largest that third derivative could possibly be, so we picked 2.3. 2.5 is the largest value on our interval, or the value on our interval that makes this the largest. And then we have our 3 factorial in the denominator. Good or no? Great. And then lastly, even though y'all are leaving here in my class, this will be posted in the notes. This is the same thing that is in that document that is like series to know. So I'll have this posted at the end of the notes. So make sure you have all, 7 of those ones memorized. Other than that, we're good. We will pick up tomorrow. If you have questions, you can stay.